So, good evening and welcome to the latest installment of the Slack Public Lectures. Today, we're very glad to have Julia Gonski, who's going to tell us actually some pretty amazing things. Julia started out as an undergraduate at Rutgers, got sucked into the environment of the Large Hadron Collider, and she's been working there very successfully ever since. She did a postdoctoral fellowship at Columbia, and that was where I met her in the midst of a huge laboratory full of trigger hardware. What a trigger is, you're going to find out. And then recently, about a year and a half ago, she came here as a Panofsky Fellow. And while she's here, she's interested in what AI can do for particle physics. Now, you know what AI can do for many things. It can do your shopping, write notes, etc. But particle physics goes in another dimension, and it has very interesting and very difficult requirements, which really test the ability of these programs. And so Julia's going to tell you how she's been trying to exploit that to solve the hard problems of particle physics using AI. So let's welcome her.
Okay, very good. You can hear me. You guys can see the slides, so I think we're set. So thank you so much, Michael, for the nice introduction, and to all of you for taking some time out of your week to come hear about science and find out what we're doing here at Slack. So as Michael said, I'll talk about this technology, artificial intelligence. Maybe you've heard of it. It's everywhere, it seems now. We can't look at a single website without seeing some connection to AI. But this is a lab, after all, and we want to focus on the science applications. So this is a great opportunity for me to talk about one of my favorite topics, particle physics, but particularly these interesting connections with artificial intelligence and how we can expand the field of AI through the study of fundamental physics. So there's a lot to get to. Let me dive right in. First, I'll start with a quick roadmap, so you know what we're starting with, where we're headed. Of course, I need to begin this conversation with an overview of the field of particle physics. Why are we still working on this? What kind of questions do we want to solve? Then we'll get into a brief overview of what machine learning is, just the basics as it pertains to particle physics research, and a particular flavor of machine learning called anomaly detection that is the focus of a lot of my work here at Slack. We'll then take that idea of anomaly detection and apply it in real time in the ultra-fast timescales of high-energy collider experiments. And then finally, looking towards the long-term future, what can we expect to see out of this field of collider physics for the rest of the century? First things first, let me motivate this whole area of research. And the way that I want to do that is to really motivate physics in general. What really is physics research? What are the types of questions that we're after? And to do that, I want to show this sort of timeline or x-axis here of length scales. So you can think about physics as a way to understand the actors and the rules of play of all of these different systems on all length scales in the universe. So at the smallest end, we have the dynamics of the particles that make up a proton. We'll talk quite a lot about that in particle physics. All the way up many, many orders of magnitude higher to the scale of the observable universe. How do all of those actors, planets and galaxies and black holes, interact with one another? Physics research has some hand in understanding the dynamics of all of these different systems. So the way I got interested in physics, and the entry point probably for many of you, lies in the center of this length scale. So the typical content you'll learn about physics in a high school course, maybe at the lowest end, you'll learn about Coulomb repulsion of the electron and the nucleus in an atom. And maybe you'll go up to, on the larger scales, things like Newtonian gravity and how planets orbit the sun in the solar system. So this is all well and good. It's fun to learn about these things. If you're into that, which I was, you might start to ask questions about what lies beyond this box. Do the same rules apply, or is it a different picture? So if you go to the lowest possible scales, you're asking a question like, if I break everything down into the smallest possible level, what are those things that I cannot break down anymore? Those are the most fundamental pieces of the entire universe. That would be a fundamental particle model. The list of things that are, you cannot get down any farther than that, and the rules by which those things interact. And what's interesting about trying to build that fundamental particle model is that everything else on this scale, every other system up to the full scale of the universe, is made of the same stuff. If you really got every single fundamental building block understood in some theory, it would connect to everything you see in the observable universe. And so there are some other types of sciences that come into play here. For example, the dynamics of galaxies or fusion in the sun. You have to pull in some chemistry there. But even on a universal scale, there's a lot of fundamental physics that dictates how massive processes elapse in the universe. So that you automatically ask this next really interesting question: what does that fundamental particle model tell us about the largest possible scales? Things like the origin and the evolution and the fate of the universe, right? No big deal, easy things. And so if we had a good fundamental particle model, if it was comprehensive, it would be able to also inform what's happening on the largest scales. And so this really is the goal of the field of particle physics, is to observe with experimental data and characterize and understand all of those fundamental building blocks into some nice, neat, organized, comprehensive model. And so we're doing pretty good at that so far. In the past several decades, we've been working on building up such a model. And this is where we are at present, with the standard model of particle physics. So each element in this table is a fundamental particle. It is not made of any more things. You have broken it down as far as you can go. And it can be organized in this nice, neat tabular format. Maybe it reminds you of a periodic table from chemistry. And the location of particles in this table gives you a bit of information about what kind of particle they are. On the leftmost side of this table, we have all of the matter, all of the stuff that we know of in the universe is made of just these set of particles. Me and you and this table and the room and the atmosphere are all made of just that small set of matter particles put together in different ways. The next column here are the force-carrying particles. There's a particle for each fundamental force, things like electromagnetism, the different ways that particles communicate with one another. Those forces are exchanged through the passage of one of these special force-carrying particles. So this is the communication part of our fundamental model. And then finally, off here on its own is the Higgs boson, which is off on its own for good reason. This is a unique particle in the standard model. It is responsible for a couple essential features of our universe, namely, it's the reason that particles have mass. So you can imagine we won't have much of a universe without anything having mass, right? And it's the most recent addition to the standard model. So that's where I really want to start the story here, is with the Higgs boson. We can use this as a use case for how particle physics research gets done. So the Higgs boson, as I mentioned, has a unique role to play, and it was the last predicted particle in the standard model. That table was assembled over decades through a process of theoretical prediction. So the mathematical formulas of the standard model would say, we expect there to be a particle here with these properties. You can go off and experiment and find it. You can do that iterative process several times, and the Higgs was the last example of that, the last building block to fall into place. It was observed at the CERN laboratory in Geneva, Switzerland, which I'll talk more about, in 2012. And that was nearly 50 years after it was first predicted by the mathematical formulas of the model. And so naturally, if you wait 50 years for something that finishes a model of fundamental physics, you're pretty excited about it when it turns up. And I think the best way to look at that is through things like the Nobel Prize that was awarded the following year for this discovery. The New York Times and lots of news outlets picked this up. And this image at the bottom here is from the New York Times. This is a picture of the auditorium at CERN after the announcement of the discovery of the Higgs. So before we get into any of the science, right, you can see the sheer human aspect of this, right? That people have been waiting so long and working so hard, and this really significant moment finally comes through for the field. I also like to start my story with the Higgs boson, because this is where I turn up in the field of particle physics. So this is me, the first time I ever went to CERN. This picture was actually taken in 2013. So I was a year too late. But in 2012, I was a sophomore in college. I was doing a summer research program at the University of Illinois, working on a search for the Higgs boson. So I start this summer, June 2012, a month before the discovery, an undergraduate in college, right? And a month later, we find the thing. So you're welcome. It was amazing. I mean, it was incredibly exciting for me just to see how people were interacting, and there was so much to learn about. And this particle has so much still to tell us about the fundamental universe. So this was a really formative part of my exposure to particle physics, and I think is a large part of why I'm standing here today, talking to you still about energy physics. So I mentioned that the Higgs boson was observed first at the Large Hadron Collider, or at the CERN laboratory, I should say. This is the current energy frontier in the field of experimental particle physics, which is to say that this is the highest energy collider ever built and still operating. So this is a 27-kilometer accelerator located underground at CERN. The facility itself actually lies across the French-Swiss border. So here you can see sort of Geneva in the background, the beautiful Alps. It's not a bad place to go for work travel if you like the mountains. And what this 27-kilometer accelerator does is accelerate beams of protons in opposite directions to really high energies, very nearly the speed of light. I'm not going to say all those nines. And it does that collision, and at certain points around the ring, it will take these two accelerated beams and cause them to interact, collide them together. And it makes those collisions 40 million times per second. So if I can start to set the stage for how this is going to be a big data problem, this is a good place to begin. But why would we do something like this? What's actually happening when you send these two high energy particle beams together? Why to go to all this trouble to accelerate them so fast and collide them so many times? The secret to this, the answer to this question, is the most, I would say, one of the most famous equations in physics. Anyone, what's the most famous equation you can think of in physics? Shout one out. What's that? E equals mc squared. Perfect. Thought maybe we might have some F equals ma folks in the room, but okay, good. You guys know exactly where I'm going. E equals mc squared. Okay, but what does that mean? We know from our friend Einstein that this is important. What is the E and what is the M, right? This tells us that energy and mass are related, which is the key ingredient here. We want all of that energy in a small collision point to turn it into mass. And when I turn it into mass, I stand a chance that in the roll of the quantum dice that happens when two particles interact, I can produce something interesting, maybe something new. And so what actually happens when you put all that energy into one focus place is you get a lot of mass out. And that means that when those particles collide, they produce a lot of stuff, a spray of different species of particles in different locations at different energies. A lot of complicated particle physics happens after that initial moment. So this is interesting to me as a scientist, right? I want to be able to measure what happened in this collision so that I can maybe understand the key rules of how these particles interact and talk to each other. And so in order to take advantage of all of this information, I need a really complicated camera. And that's what the detectors are. So every place where these particle beams collide, we build a complex multi-subsystem detector around those interaction points, whose job it is to collect all the information about what particles are produced in that collision and allow me to reconstruct the event. So this is a picture of the ATLAS detector, which is one of two multi-purpose experiments at the Large Hadron Collider. And this is turning those particle tracks into data that I can analyze later. So these are complex and really staggeringly large experiments. So here is a guy standing here for reference. If you ever get the chance, you're in Geneva and they're not running the accelerator, you can go see these things. It's extraordinary. You walk through the edges of this detector and there's just millions of channels of cables coming out of this thing. It's really extraordinary as a piece of scientific infrastructure. And so this detector is designed and built carefully so that I can uniquely identify all the particles produced in my collision. And again, try to peer back to that initial moment when those protons first collided and understand what could have existed there. And so a lot of the time when two protons collide, I know what's going to happen. They obey the rules of the standard model. So I know that most of the time they're going to produce two quarks. Some of the time they'll produce some leptons. They can produce different species within that model. But that's not the only thing that I'm interested in. In fact, I'm mostly interested in what happens when those beams collide and something happens that I haven't seen before. So why do we think that there might still be things happening in these colliders that we haven't seen before? To answer that question, let me go back to my diagram of all of these different systems in the universe, right? There are quite a few things that we know exist in the universe that don't fit into the model. And things that keep people like me up at night, right? Things like gravity. I mentioned that there is a category of force-carrying particles. Gravity sure is a force, standing here, right? There's no force-carrying particle in the model that mediates the gravitational force. We know gravity exists. We have gravitational waves and general relativity, but we can't get it to talk nicely with the fundamental particle model. It's a similar story for dark matter. We can take data from the rotation curves of galaxies in the universe, and we know that there is more matter interacting gravitationally than we can see. It's not visible. It doesn't interact with the photon, with light. There's no particle in the standard model that explains this behavior, but we know that it's out there. And then finally, on the smallest scales, I mentioned the Higgs boson has a unique role in the standard model, and it actually opens the door to many more questions about the model that we don't have answers to. One of the most notable is that the Higgs boson is very connected to the nature of our universe and whether the vacuum of our universe is stable or unstable, which maybe can sound a little nerve-wracking. It's interesting to try to understand these types of things about where the universe is evolving and what is the ultimate fate. So there are many more questions like this. These are just representative of ways in which the standard model is great and has gotten us far, but is not finished. And so the field of particle physics now has to address this. We have to ask the question, based on topics like these, we know there must be physics beyond the standard model, new physics that we've never seen before. And we want to find it, because that's our job, is to make that model comprehensive. So that brings me to the actual techniques, right? And then we'll actually get into the machine learning side of things. So when we talk about looking for new physics, I'm going to mine these 40 million collisions a second and all the data that comes out of my detector to find some hints of something new. It kind of feels like this. So you're familiar with this game if you were around in the 90s. If you weren't, this is how we used to have fun before the internet, which is that you would have to look at this picture and find this guy, Waldo. Does anyone see him? Do you really see him? You're going to ruin my point. Okay. So maybe the very eagle-eyed of us. Oh man, people are veterans at this. So for those of you who haven't found this character yet in the picture, let me make it easier. I'll remove half of them. Any extra observations? Not quite? Okay, I can keep making it easier. I'll keep removing parts of the picture where he is not until eventually, okay, there he is. He's a little pixelated, but he's there. Like I said, it was the 90s, so. Those of you who thought you found him, was this where it was? No, okay. So we needed data analysis, perfect. So how was I able to do this? It would have taken you forever to just look through the picture. There are two important features of this process that made it easier to find your signal. The first of those is that it's easier to find something rare if you remove the background. You want to increase your signal to noise. So if he's just one character out of 7, it's much, much easier to find what you're looking for. And that applies also to rare phenomena in the particle collider. Another important thing that let me do this as quickly as we did is that I knew what I was looking for. I knew that he's a little guy with a red striped sweater, he's got a little hat, right? And if I didn't know those things about Waldo, this would have been really hard. I tell you to find somebody, but I don't tell you what he looks like. It really ups the challenge. So particle physics is just like this, really. We have a huge amount of information coming out of these detectors, but we're only interested in a couple types of collisions, the ones that maybe give us hints about where your dark matter is, or what is gravity, what is the particle nature of it. But I have to sift through a lot of background to get there. So to give an example of how this works in the collider, this is a type of event that we get out of that initial collision. This is an actual simulated event display from a real proton-proton interaction at the LHC. And this is a particularly fun one to show because this is a data event where it was suspected that we had a Higgs boson. And so all these different colors and lines and different pieces of the detector are places where a particle interacted with a piece of that detector. And through our data acquisition process, we were able to turn that particle interaction into zeros and ones. So we could do this reconstruction of the full picture. And so I know that my Higgs goes to these two B particles. I know what a B particle looks like. I know what the pattern looks like in the detector. I can use that to pluck this one event out of the background. But this is harder than the Waldo situation, believe it or not, because the Higgs only is produced in 1 of a trillion collision events. So there's a lot of background to cut away. And we have to use a lot of intelligence in designing the methods that select the signal and reject the background. So with the Higgs boson, this is doable. And in fact, we did it, right? We were able to discover the Higgs at the LHC. But when I'm talking about new physics, physics beyond the standard model, it's not so simple. Because what if I don't know the characteristics of this new physics? I don't know what particles it decays to. I don't know how it interacts with my detector. So now I'm faced with these, trillions and trillions of particle events, and I want the ones that look unusual, that don't look like the standard model, but I don't know what to tell my analysis strategy to use as a selection method. So this type of problem introduces this specific application where I may have new physics in some of these, but I don't know how to isolate my signal, of artificial intelligence. So here's where the machine learning part comes in. Machine learning and high-energy collider physics have had a sort of natural relationship for several decades. And that's because these data sets produced by machines like the Large Hadron Collider are pretty unique data sets in the world. They are very large. We have tons and tons and tons of these events. That means that there's high statistical power behind those data sets. And they're also pretty complex. Lots of different features. Think about all the cells that were lit up in that event display in my detector. And all of those complex features are correlated because they come from the same underlying process. So this is prime for your artificial intelligence and machine learning applications. So this isn't an AI talk. I won't really get deep into the math of how these things work. But for the sake of understanding how it applies to analysis, we want to think about some type of machine learning tool that will take in information about my collision event, learn something fundamental about what these events are like, such that I can query it on the other side. I can train my model, and then I can show it a new collision event and ask it a question, like, is that event, does it have a Higgs boson in it? Is that event background? Is it regular standard model stuff? I've already seen it before. Is it detector noise? Is it a fluke? Is it a cosmic ray? There are many different kinds of questions that I might want to ask this highly intelligent model about my data set to enable the analyses that I'm interested in. One more note about this symbiotic evolving relationship between AI and physics. I would point you to the Nobel Prize in Physics in 2024 was about machine learning. And in fact, it was awarded to Hopfield and Hinton for foundational discoveries and inventions that enable machine learning with artificial neural networks. So machine learning is born of physics principles, and it feeds back into the development of new physics principles. And so there's this natural connection between these fields that has been really fruitful, I think, for both of them. So I mentioned anomaly detection in my outline, and it relates back to this question of how do I find new physics if I don't know what I'm looking for? So what is an anomaly and why do I want to detect it? Anomaly detection is a particular flavor of machine learning where you are able to identify unusual elements within a data set. Not because you know why they're unusual, only because you know that they don't look like the background distribution. You know what a regular event looks like so well that you can distinguish any type of outlier only based on that background knowledge. So in this case, you imagine that you have a lot of events that look standard, but there's maybe one or two outliers, and that's where we think our new physics might be hiding. So how do I actually implement this in terms of machine learning? So the first thing you have to do when you develop a machine learning model is train it. And you would use a large number of events of some distribution that you're interested in to update the weights of this model. And that just allows you to execute some algorithm with these particular weights that have come from learning about the distribution. Once you're done updating those weights and updating that formula that will run on each input, you can evaluate it over new elements in the data set. So let's say you train over a school of fish, as one does, and you want to now evaluate on elements, new elements of that data set. And the shape of this architecture that I'm showing you is particularly relevant to how I want to do my anomaly detection task. I'm going to build a model that will take in a fish as input and generate a fish as output. And I want that output fish to look as much like the original fish as I possibly can. The way that I'm going to motivate my model to do that is by squeezing the amount of information stored about that original input as I'm training. So this lower dimensionality is a lossy compression of all the input features that I use to describe my fish. And that is forcing my model to learn the minimal amount of information needed to reconstruct something realistic. And as I am training and training, I'm asking my model to get better and better at making more realistic fish. So by that time, you train over a series of fish, it knows how to produce a fish that's blue. It's seen it a million times, it's stored that information in the model. It knows how to produce a fish that's swimming to the left, store that information in the model. So if the question that I want to ask my model at the end is, are you anomalous? For each new event that it's looking at, it's going to say, no, I've seen these before. I know how to generate these features. However, if I then show it the rare element, the one that my model hasn't seen a lot in training, it doesn't have the information stored in the weights of my model to reproduce red. It doesn't have the information stored to reproduce a fish swimming to the right. So when I ask it that last task of generate an output for me that looks like the original, it completely fails. Can't be done. It'll generate some output that looks nothing like what you wanted. And that is my flag. As I'm evaluating new events in my data set, if one of the reconstructions fail, I'll say, great, that looks like an anomaly. It doesn't look like what you've seen before. So this is exactly what we want in terms of data analysis. I could build such a method that will fail to reconstruct rare elements and then assign a score related to that reconstruction success to each element. The normal ones will represent the bulk of a distribution that are well reconstructed, and any rare events will have a long tail in this distribution out to worse reconstruction performance. And I can select on that tail of the distribution to isolate my anomalies, to enrich my signal to noise for anomalous events. So this is all well and good for fish, but that's not what we're here to talk about. We want to talk about jets. So a jet is a particular type of object that you get in a high energy particle collision. In fact, it's one of the most common things that we produce at the LHC. And it is a spray of particles coming out from the initial interaction point that is originated by a quark or a gluon. Those are just two of the actors in that fundamental table. And so what I look at in my event, if I want to recognize a jet, I will look for this cone-like spray of particles coming from the interaction point. And I can run a clustering algorithm to say, okay, a couple of them are close together, they fall into this cone shape. The result of that clustering gives me this jet object. So super common in the collider, like I mentioned. We're also interested in them because they are a very common decay mode for potential new physics. Any extensions to my model that may include a dark matter candidate or high mass new particles or solve some other problem with the standard model often have very strong couplings to jets. So lots of searches for new physics rely on reconstructing and analyzing events that have these jet objects in the final state. So that makes them a great target for anomaly detection. And then let me get a little bit more specific about this idea of building a model to reconstruct my input. The actual model that we use in these contexts is called an autoencoder. So this is essentially just two basic, fully connected neural networks stuck together. The two stages have one first stage, which is the encoder. That takes in your input modeled by some set of features. Maybe it's blue swimming to the right, right? Things we saw in the fish data set. And then it reduces information by restricting the number of values you can assign to that input. So here I go from 6 input features down to 2. I've lost some information, but that's part of the process. Because then my second stage decoder network will sample from that lower dimensional representation and try to produce an output of the original dimensionality. And so the way that it gets better and better at doing this reconstruction is by training with a loss function. This is the only equation I'm going to show you in the whole talk. So it's an easy one. So the loss function is the rule that you give your machine learning model that tells it how to learn, that tells it what to learn. The loss is a quantity that your model will calculate for each new input you show it, and it is motivated to minimize this loss function. So in this case, my loss will be the values of the output nodes minus the values of the input nodes, the reconstruction error. This is a proxy for the quality of my reconstruction. And remember that the better the reconstruction is, the more normal my event looks. So let's see how this actually applies to this scenario of looking for anomalies in the data with jets. My background jet, this cone-like cluster of particles, has certain features that I know about because it obeys the standard model rules. So this type of jet originated by a regular standard model particle will have a pretty even spray of particles that are generally evenly distributed across the cone, and the energy will not have any hotspots or localizations. However, the types of jets that come from new physics, that come from new particles, may have some weird features in the energy distribution within my cone. Maybe I will have 2 or 3 particles sort of overlapping within that cone, and I can detect those hotspots within the energy distribution. Or maybe, like this last example, some of the particles in this jet are invisible to my detector. They don't leave normal signals. My regular reconstruction algorithm doesn't work. All of these types of weird jet processes could be hints of something that I want to understand better. So when I take my autoencoder and I'm using it to look at every new event that comes in at the LHC, and I'm saying, look for jets that don't look normal, that don't look like typical standard model. When it sees my regular background jet, it says, okay, I know how to produce this. The particles are evenly distributed across the cone. I got this. Even though I had to lose some information in the middle, I can produce a realistic output because I learned to store the most salient features of the jet in that lower dimensional representation. So you're looking mostly at regular QCD jets, and it says not anomalous, all normal, all good, until it sees one of these new physics jets with a weird energy pattern, with some higher areas of correlation within the cone. It will, just like with the fish, fail to reconstruct this. It'll give you different kinds of particles, energy that doesn't make sense, and when you calculate the reconstruction error, the flag goes up. The reconstruction didn't work. I suspect that this jet is not a regular background jet. So this process of tagging anomalous jets is actually really generalizable, and it's hard at work throughout the experiment. One of my groups put out the first analysis from the Atlas experiment that used this type of machine learning. It's completely unsupervised. It runs directly over data. You don't need any simulations. We didn't find anything. It would be a different talk if I snuck this on you now that we found new physics. But it's a really novel analysis method that is, I think, taking particle physics by storm, and other fields of physics as well, because the generalizability means it applies to lots of different kinds of input data in a similar way. Okay, so that is the general principle of anomaly detection, why we think it could point us to new physics, and why it's an efficient way to mine these huge data sets at the collider. You may remember this sort of third element in my outline was doing this in real time. And I mentioned that the collider operating scales are really, really fast. So to motivate why I might want to do this selection process really quickly, let me go back to the way that we produce the data that I use in an offline analysis like the one I just described. The Atlas data pipeline has 3 key stages here. At the very front end, we're talking about computational processing that is happening on the detector, turning those signals of particles passing through matter into currents and zeros and ones. Once data is sent off of the detector cavern, it goes through this trigger stage, which I'll talk about in one more slide, before it makes it to the offline analysis where we do our Higgs boson searches and our anomaly searches and all the regular stuff that takes, it's stored on data, it's stored on disk. We can revisit it anytime. And so why do I have this middle stage? Why can't I just save everything? So this trigger stage is essential because it makes a decision about each event in real time. Every single time you have one of those collisions, the 40 million collisions per second, the trigger has to make a judgment call based on what it sees. And that judgment call is, do I want to save this event to disk so that I can look at it later? Or do I want to throw it out? It sounds like maybe a crazy thing to do with a data set. But in reality, a lot of the data that is produced in these collisions, we don't it's not interesting to us anymore. It's all a statistical game. And 99.99999 times out of 100, we've seen it before. It's old news. It's in the standard model. We've already understood it. We want the weird stuff, right? We want the things that we don't understand. So to put this in more real terms, you get one of your collision events, all of these particles in the final state, and it goes to the trigger. And the trigger looks at the kinds of particles you have and where they are and how much energy they have. And it will make that call. This is boring. You don't need to look at it. Don't even bother saving it to disk. Save your breath. Or I found something kind of cool. Something is unusual or it's really high energy. I think we should save this and analyze it later. And this decision is a really big deal because of the huge volume of data we produce at the front end. We only save 0.003% of everything we produce. So the overwhelming majority of data produced at the LHC is thrown out instantly, right away. Now it's okay because it's a statistical process and we make this trigger algorithm very intelligent. We say, okay, I know what a Higgs boson looks like, so don't throw out the Higgs events. I know what a Z looks like. I know what dark matter might look like. So we have to use some judgment injected into that trigger decision to make a good call, to preserve the maximum amount of physics information in that offline data set. Okay, so that already sounds pretty hard, to throw out most of your data at this very large, expensive, once in a lifetime experiment. What makes it even harder is that I have to do it really, really, really quickly. So this 40 million collisions a second at the front end, that turns into one collision every 25 nanoseconds. So this first trigger has to take in every event once every 25 nanoseconds and make this decision, this really important decision for the whole experiment. It's broken into two stages, which I haven't mentioned yet. The first one is a hardware trigger, which I'll talk about what hardware is and why we need to use it for the really fast part. We then send it to the slightly slower version of the trigger. We've already reduced some of the data rate. The software trigger has about microseconds to a millisecond to make its decision. And then finally, every 1 millisecond, we're writing an event to the final stage storage. So nanoseconds, microseconds, milliseconds, these are a lot of different prefixes. How fast really am I talking? Really fast is the basic answer. The trigger algorithm running in just a few nanoseconds after all of the other processing that has to be done in this trigger is very little time. It's so nano as a prefix is 10 to the minus ninth, a billionth of a second. So for a little bit of reference, human reflexes are typically about a millisecond, which is a thousandth of a second. And a camera flash is about a microsecond, a millionth of a second. So we're talking 1,000 times faster than a camera flash. We have to be able to do some type of data processing over the signals that I get out of the detector. So what kinds of decisions do I want to be able to make? And what algorithms do I want to use to do those? In the dream world, I could take this ability to isolate outliers in the data set and apply that to this real-time decision. And the reason that we might want to do that is because there could still be new physics hiding somewhere in this experiment. We know we haven't found new physics since the Higgs discovery, but we have good reason to believe it's there. Maybe we don't see it yet because we've been throwing it away in this 99.999% of collisions that we don't ever get to look at. So this is a basic cartoon that describes the type of event that we save with our existing vanilla old-fashioned trigger menu, which is essentially based on energy. Remember the E equals MC squared, right? So if an event has a high energy scale, it has final state particles with a lot of energy, those are more likely to be something that I want to save to look at later. More energy, more mass, interesting stuff. So most of my existing trigger algorithms use energy as a pretty blunt proxy for level of interest. I look at an event and I say, was there a high energy particle in this event? Yes or no, I can calculate that super quick. And that lets me curate the set of events that I want to record to disk. But nature may not be so kind, right? It may not be populating those high energy events only. Maybe there's new physics hiding below those energy thresholds, which means I've been producing it at the experiment for 10 years and I've just never seen it. So this is where artificial intelligence and anomaly detection in particular can come in. Maybe I had all kinds of anomalies at these low energy scales, and they've been going to the trash can side of the trigger algorithm and not to the save to disk side. So our whole data set, we've just been removing them by having to make this simple, fast decision. So I know of a way now to avoid this. It's the autoencoder. I can train my autoencoder, evaluate it over events in real time, and use the autoencoder to raise that flag of whether something is anomalous, and maybe I want to save it for more scrutiny later. So the idea of real-time anomaly detection is that I will build this fast trigger decision algorithm based on the autoencoder, and that will allow me to probe below those energy thresholds and unlock a whole new set of events that I've never seen before, ever in high energy physics. So there's a lot of potential to this, and it may really unlock windows into new physics with potential discoveries that we've never had a handle on before. So the motivation is clear. We really want to be able to do this. The technical challenge is, can I run that autoencoder in less than 25 nanoseconds? I told you the previous algorithms were just, what's the energy? Which is much simpler than all of those multiplications and nodes that I showed you in the previous section. So when I first started working at SLAC, there are really excellent electronics and firmware engineers here. And I told them I wanted to run an autoencoder in 25 nanoseconds, and they laughed at me. They said, it's impossible, can't be done. Spoiler alert, we figured it out. But let me tell you the story and then show you how to get there. So we're going to take a quick detour. Keep the physics motivation in the back of your mind. All of this discussion about running things really fast, what does that mean, really? What is running something in a computing sense? What those algorithms are in machine learning, when you send in an input, a set of features represented as numbers, and you're doing some multiplication to turn them into that decision, you are doing digital logic. If you break all of those operations down, you are sending zeros and ones through really simple logical gates. And you can build all of the most complicated mathematical algorithms out of these binary 0 and 1 gates. And computation, in the simplest one-sentence explanation, is doing all of that binary logic on a set of transistors in a piece of electronics. Nowadays, it's mostly in silicon, the type of logic device in your PC or in your phone or in your car is mostly some type of silicon-based logic tool that can run this digital logic and do math and turn it into answers for you. So if we want to really push the boundaries on this ultra-fast machine learning, I need to pay very close attention to the platform that my machine learning is running on. And so you have this nice cartoon here of a variety of different computing platforms oriented on this axis from the most flexible logic platform to the most efficient. So on the leftmost side here, you have your CPU, your central processing unit. This one you're probably familiar with. It is a classic computational architecture, really optimized for calculations in sequence. And a CPU is completely flexible. On your laptop, you can go from a text editor to Photoshop to an internet browser seamlessly, right? You can do whatever you want with it. As we move away from the fully flexible, we have things like GPUs, or graphical processing units. If you're an AI-minded person, you're probably, or a gamer, I guess, actually, you're probably familiar with these. They are optimized for parallel calculations, which is to say that I'm doing multiple calculations all at the same time. And that's something that's really useful for rendering images in video games and movies, but also for evaluating the different nodes in the layers of that machine learning calculation. Now maybe we get to the more exotic ones that are a bit less familiar. you have a field programmable gate array, or an FPGA. This is, you can buy, I mean, there are lots of companies like Xilinx and Intel that make these things. They're still just computational platforms, but they're a bit more specified. You're losing that complete programmability of the CPU in that the FPGA is composed of block resources. So all of the different parts of your computer that you can use to do various pieces of your mathematical calculation, the FPGA will say, okay, this corner of my piece of processor is optimized for multiply and accumulate. This corner is optimized for small bit width, little additions and subtractions, small numbers. That removes some flexibility because I can't ask the addition part to be a multiplier. It doesn't work. It's already been prescribed as that. But what I trade is higher efficiency. I don't need to reprogram every single logic gate every time I send it a new algorithm. And efficiency turns into lower power and higher speed. Okay, we're getting warmer, right, on my super fast autoencoder dreams. The last one on this list is the application-specific integrated circuit, which is application-specific, as you maybe guess. And this is a scenario where you take some mathematical algorithm you want to run, and you actually etch it into a piece of silicon. It only runs that algorithm. You have damaged the computing platform to only run a very specific sequence. So these ASICs, they are etched into raw silicon. This is a piece of one of these multi-project wafers. Maybe you hear about these specialized foundries in Taiwan. Maybe you couldn't buy a car because there was a disruption in the chip supply chain, right? You certainly have an ASIC in your phone. I mean, they're everywhere because they're highly efficient, super fast, very low power. So when I'm thinking about any application, this fast trigger machine learning algorithm is one, but anytime you want to think about running a machine learning process in some type of constrained environment, you want to think about the platform that you're using to execute that algorithm. So the general rules, if you have very high throughput, so huge volume of data per unit time, okay, Collider, check. Low latency, if a GPU can probably get you to a millisecond, but not much faster than that. Okay, we're a million times faster than that, so check. And low power. This can also turn into greener AI outside of the physics context, which is exciting, and I'll circle back to that. So there are a couple other tricks that I have up my sleeve to do machine learning fast. And if I really want to optimize my machine learning implementation for particular constraints, whether they're power or they're ultra fast, I need to minimize the amount of computation that I'm doing. Fewer zeros and ones going through those gates will give me a more efficient implementation. So there are some ways that you can work with your algorithm to optimize for this scenario. You can remove some of the nodes of your model in what's called pruning. So this is the type of model that I showed you earlier, one piece of the autoencoder. I can actually go look at the values of the weights of each of these nodes and realize that some of them are really small. They're not contributing much to my final answer. So my final answer probably will be pretty accurate if I just remove a bunch of them, and that saves me time. It makes my calculation more efficient. Another trick is to quantize the numbers that I use to represent the values in my model or the weights of the model. All these different numbers that have to get multiplied and added to evaluate the network. So quantization refers to the number of bits of zeros and ones in a binary representation of a number that I use to describe the value. So you can fix the number of bits that describe this number, and you can make it more coarse-grained. I can remove information. Now it looks like Waldo, right? After I do some pixelation. But again, maybe that's fine. Maybe it gets me close enough to the original value within my performance requirements, but I had to put fewer zeros and ones through the math. So there are other types of tricks you can do to make machine learning more efficient and run faster. But let me put all the pieces together and bring it back to this question of running the ultra-fast autoencoder. We apply both pruning and quantization to the autoencoder to fit it in the trigger constraints. In terms of pruning, we actually got rid of half of it. That's how efficient the information storage can be in these models if you optimize for fewer resources used. So we end up training with the full autoencoder, but we only use the first part of it on evaluation. And enough information about the anomalousness of my inputs is stored in the latent space in that lower dimensional representation that's all I need, as it turns out. We do also quantize all of the values down to 10 to 15 bits, depending on the layer. And after a lot of hard work from many folks in the group, we get down to a latency of less than 25 nanoseconds. So we were super excited about this. It means that we are on track to put this algorithm into the Atlas trigger for 2025 data taking. And again, this means that we are going to collect a set of events from this experiment that we've never seen before. It's like a completely new experiment. And of course, we'll be first in line to have a look at those events and see if we can pull a Nobel Prize out of them. We'll see what happens. Okay, so there are lots of different ways that we are working on this idea of efficient hardware platforms, specifically to run machine learning. We focus on the physics context, but as I said, there's lots of applications to this. So SLAC, combining the physics and the engineering and instrumentation areas of the lab are leading a lot of R&D efforts into new machine learning optimized hardware computing platforms. An example of this is an embedded FPGA or an eFPGA. This is a sort of new technology that's somewhere in between an FPGA and an ASIC. You're putting those FPGA block resources into your silicon die of the chip. So you kind of get the best of both worlds. Google is actually picking up these eFPGAs as accelerators in their offline computing system. So these benefits of faster, lower power ML are really across the board. So this is a nice picture of some of the group that's working on this in the lab just a couple buildings over. Kenny, who's a PhD student at Stanford, who is here, so you can ask him questions later about this, and one of our fantastic engineers, Larry, in the Technology Innovation Directorate. So I've talked a lot about how this doesn't just pertain to physics. And so let me back that up a little bit by talking about what the industry is doing in terms of intelligent, optimized electronics. So NVIDIA had a good year. It hit $3 trillion market cap, became the highest valued company on the market. What is NVIDIA known for? GPU production, but also R&D into new platforms. Because you can bet if I could find a way to do more machine learning in less time for lower power, which is cheaper, and a company like NVIDIA is going to be on it. There was another article here about Sam Altman, who was in the United Arab Emirates looking for investments in microchip foundry technology. So I mentioned that these super sophisticated nanofabrication facilities that produce today's chips, the bulk of that industry is in Taiwan. And it's a huge, highly, highly valued technological industry. And again, people have eyes on this. People would like to have more of these foundries, building more specialized devices, getting to lower feature size in these technologies. There's a lot of R&D that could, again, save people money and time in advanced computing. And then finally, the last headline I wanted to mention is that all of the computing that I've spoken about so far is related to current traveling through silicon, a current of electrons. And electrons are pretty fast, but they're not speed of light fast. Only a photon can do that. So there's actually new efforts to develop photonics-based chips. Again, thinking, how can I save time? Let me get rid of that pesky time that an electron takes not traveling at the speed of light. And that in and of itself can save you time in just passing current through different areas of a chip that can run an algorithm. So I think this is a really exciting technological area. Of course, physics is our development use case for it, but the industry is certainly going to be on it. And I think we'll really see our AI potential as a society change as these tools become more sophisticated. Okay, so my last few minutes, I just want to talk a little bit about the future of collider physics. We'll bring it back to the colliders at the end here. So the LHC has been around for a while. We're going to have it for quite a few years still to come. And this is the rough plan for the operation of this accelerator. You can see we iterate back and forth from a run period when we're actively colliding these protons to a shutdown, where we install some upgrades to the detectors, we replace things that have been damaged, we clean the detector up and get it ready to go for better operation. So all the way at the beginning of this talk, I started with the Higgs discovery in 2012. Of course, here we are today at the end of 2024. We are in the middle of a run period now, but we are coming up soon on a long shutdown where we will install a next generation LHC called the high luminosity LHC. So luminosity is the number of collisions per unit time. You can see when you have more collisions happening in each one of those beam interactions, you have a lot more information in your detector. This is hard to manage from the data analysis perspective, but it's good for us because we want that rare stuff. We want more chances to produce the really uncommon anomalies in physics. Then we'll have the high luminosity LHC for 10, 11, 12 years. And around 2040, we will see the end of the LHC. It can't run forever. We'll have to shut it off someday. So then what? I think I've made you all collider fans, I hope, in the last hour. You're probably thinking we need to have something ready at the end of the LHC. And 2040 may seem far away. To me, it feels like tomorrow because these machines are very big and complicated. You need a lot of international agreement and design and R&D to build and operate such a machine. And so we're already starting to think about what comes next. There's a particular proposal that I'll mention, although there are many on the table, which is the Future Circular Collider. This is the proposal put out by CERN to take advantage of that existing CERN infrastructure. And it would be a 90-kilometer tunnel at the CERN site. And to get an understanding of how big 90 kilometers is, the LHC is 27, remember, and this machine makes it look like a toy. So it's a wild civil infrastructure project. It goes under Lake Geneva. It would go under the mountains near the Alps. So just a really wild concept. And it would host two different kinds of collisions. First, an electron-positron collision, which is a slightly different kind of collision data that you collect. It's a little bit more precise. We would run that for 15 or so years, take it out and install proton-proton back to our sort of meat and potatoes collider experiment and try to push the energy frontier even higher. So I mentioned that it takes a lot to get such a project approved. It's big, it's complicated, it requires thousands of people. And there's a lot of work actively ongoing in the community now to make this happen, to realize the FCC. So this is a nice picture of the Director General of CERN, Fabiola Giannotti, and Deirdre Mulligan, who, when not working her day job, is a professor up at Berkeley. She's the Principal Deputy Chief Technology Officer at the White House in OSTP. So this was a picture taken from an agreement that was signed between the White House and CERN, indicating the US's interest in participating in the FCC facility. So data taking for this project would start in 2045, which I think, like I said, maybe seems long, but I think there'll be so much exciting work with results coming out of the LHC and in preparation for this machine. And it really calls for a next generation of leadership. So if there are any, young folks that are thinking about going into particle physics, yes, do it. You have this machine waiting for you when you finish school. Great. So that brings me to my conclusions. I really think it's a great time for particle physics. I feel like I end up advertising this field a lot, but I really do think that it has so much to offer in terms of fundamental physics potential and all the analyses that remain to be done at the LHC, any one of which could lead to some era-changing discovery with these anomaly detection tools. I've also talked a lot about the cross-cutting technology impacts of doing that kind of research at the frontier of science, particularly with AI/ML development, as well as microelectronics and new ways to run more efficient AI. And then finally, these exciting future collider plans that need a next generation of leadership. So I think with all of this put together, we have a whole century of exciting work and potentially discoveries to come out of collider physics. Thank you.
Okay, well, thank you very much for a very stimulating talk. I'm sure there are questions in the audience, so we have time for questions. Let me just tell you the way this will work. Raise your hand and get recognized. There are people who are going to run microphones to you. This session is being recorded, so please wait for the microphone before you ask your question. And I guess there's a very eager fellow in the front row.
Thank you for a wonderful talk. It was terrific. It was just very, very superb. So you mentioned 3 areas for new physics, one of which was vacuum stability. I'd like you to say a little bit more about vacuum stability. Is this related to vacuum energy or something else?
Yeah. So how deep can we get into vacuum stability? The theorists in the room are smiling. Yeah, essentially thinking about, so the Higgs boson, any of these bosons, in fact, we can think of as a quantization of a field that exists throughout the universe. So one such field is the Higgs field. And you can think about, when I say that it gives particles mass, it's that particles, just by existing in the universe, have to be traveling through that Higgs field and acquire some mass. And so when we're talking about stability, as is informed by the Higgs potential, we're talking about whether that vacuum remains in the state that it is, it remains with its current properties and behaves with particles the way that it does now, or whether that can evolve as the universe is evolving. That's the qualitative, yeah. If you want to add anything.
Very good. There's a question here, and other people, please raise your hands and I'll come to you. But let's start with this phone.
Thanks so much, and fantastic talk again. I loved everything about it. I did have a question, several questions, so I'll try to limit it to one. When you were talking about the workloads and the different types of, so comparing, for example, what it would be like to run on a CPU versus a GPU versus ASICs or something. Mm-hmm. Do you know, are the workloads, the current workloads, compatible with quantum computers only in the sense that we'd be talking about simultaneity there? And I kind of wonder if simultaneity would then change the models that we're using, or are those completely incompatible?
Sure. So yes, quantum computing is a whole interesting other element that didn't make it onto the cartoon because, as you're probably familiar, it's a sort of developing technology. As it comes to applying to the collider data acquisition scenario, the sheer volume of these computations means that they're way beyond sort of current size or stability of quantum computers. But there are efforts, sort of active R&D into, just like I was showing how you modify the machine learning algorithms to prune or quantize for your hardware application, you can similarly tweak or optimize the mathematics of your machine learning model to adapt to the quantum computer platform. So quantum machine learning is sort of its own area of R&D, but like I said, the real limitation there is how many zeros and ones can you fit in the model, and the stability of quantum computers keeps that number too low for an actual application in this scenario now.
I wonder then if that would change how much of the 99.9997% of data that gets thrown out, if that would maybe change how much data gets handled at the time.
Yeah, I hope so. I mean, that number is really defined by how much we can store. And that is pretty much defined now by dollars. I mean, a lot of it comes from dollars, but there is also R&D into more efficient ways to compress and store. To compress and store data. Yeah, thank you. So if you could store it in like a lower dimensional representation that is somewhat lossy, but maintains most of the fidelity of your original data, then you can store more data in the same storage for sort of less cost. But of course, as time goes, we'll also just come up with more efficient computing and storage. And as computing evolves, physics sort of keeps pace, and we can imagine that both our data rate and our storage capabilities will also evolve with the field.
Hello. Thank you so much for the presentation. I was just wondering, why did you have to use FPGAs and make it run so fast? It almost is as if you wanted to do it in real time. Why not just use the data and make something like a big supercomputer with GPUs or TPUs and just run it on the data after that?
Yeah, so this is really a throughput question. So the reason that we do this triggering process is somewhat unique to collider physics. One, I didn't actually give the data rate, but we're talking terabits a second coming off the detector. And that's only going to get larger. With some of the future colliders that we have in mind, it's exascale. And so there's no feasible computing farm. Again, thinking about the speed, because you still have those 25 nanosecond collisions. That you can't do anything about. That's set by the experiment. So you couldn't use GPUs because they can't evaluate fast enough. A farm of FPGAs, there's a bit of a technical hiccup, which is that it takes a lot of time to send information in and out of those. So right now we don't cluster FPGAs so well. So in terms of data volume and that issue of bringing those collisions in every 25 nanoseconds, we are a bit stuck there. I will say that the fact that we can throw out 99.99% of events is unique to the collider, because we're working with statistical processes. We know that we're producing, if a Higgs boson is 1 in a trillion, but I can still rely on it coming up every once in a while. Our friends over at the LINAC coherent light source here at SLAC also have huge, hundreds of gigabits a second data rates, but each of their experiments is unique. So they can't throw out most of their data. It's not a statistical process. So there are different types of DAC constraints that lead to different types of DAC systems. Sometimes you want to just brute force, like throw a bunch of computing at it. Sometimes you can do something like, fast rejection. Many different flavors of DAC solution in physics to work on.
Thank you. I just had one more question. It looks like you used a GAN algorithm, a generative adversarial network. What type of GAN did you use, and how did you come about deciding what type of GAN you would use?
So the super simple story that I told technically doesn't have the GAN in it. The second part of the autoencoder is generative in that it is increasing the dimensionality. It has to come up with some new information. So there's a generative piece of it. In fact, some of the folks in the group are working on a version of an autoencoder that is informed by an adversary, where you're having an adversarial network guess whether an output is original or autoencoder produced. And that can help to sort of fine tune the performance of the autoencoder, though once you bring in adversaries, it can be tricky to train. They become a little unstable. So you have to be willing to play with it a bit more to get it to work.
Thank you very much.
Yeah. Thanks.
Are you planning on implementing your technology in just Atlas or other experiments like Phaser at CERN?
Great question. So I talked a lot about Atlas. We do have a sister experiment across the ring, the other multipurpose detector, CMS, and they have actually beaten us to this anomaly trigger thing, which frustrates me because we're better, obviously. So yes, everyone in particle physics is thinking about FastML on FPGAs. And something like Phaser, which is one of these sort of smaller scale auxiliary detectors, also at CERN, but off the beamline, a little bit more specified, has the same constraints, as in you're in the radiation environment of the cavern, you have a fast collision rate coming. And so I don't know specifically if they're using ML and FPGAs, but it is broadly used across these real-time high data rate experiments.
Would it be applicable to, like, would you be able to use the same sort of technology for all of the different like parts of CERN?
Generically speaking, if your system has an FPGA, I don't, not to speak too strongly to it, but you can probably enhance whatever algorithm you're running on that FPGA with an artificial intelligence approach. So I think essentially, once you get to the ASIC level, it becomes a bit trickier, but the FPGA stuff that I'm describing is pretty generic to use.
You know, you mentioned there is a lot.
Sorry.
You mentioned there is a lot of background noise from the pollution. Has there been any effort to reduce that noise?
If anything, we're only going to scenarios where there's more background, actually. So background is one of these sort of unfortunate facts of life, which just come from the fact that we want to go to higher luminosity because we need more rolls of the dice. If we want the super rare stuff, we just need to produce that many more collisions. So in that sense, if you want the good stuff, you have to produce a lot of noise. Maybe the one exception is what I mentioned at the end very quickly are these E plus E minus colliders. They're point particles, whereas protons are actually composite. They're made of stuff. When you collide point particles, there's a lot less going on in your collision environment. So the number of final state particles is fewer, and that's why we can make better precision measurements because our reconstruction is that much more accurate based on the detector signals.
What is the certainty that the actual collision causes this background noise? Because there's other ways there can be noise. So.
Oh, yes. There are many kinds of background in the experiment. When I talk about you collide two particles and only standard model stuff comes out, that is a physics type of background. But there are also, one of your calorimeter cells lights up for no reason. It's noisy or it dies. And your reconstruction can be inaccurate because your detector there's detector background. There are non-collision backgrounds, like there are, constantly cosmic rays coming from the sky, neutrinos passing through you all the time. Some high energy muons can just pass through the detector. The detector is designed to reconstruct muons, so it will find them. That's another type of background. So it sort of comes back to this low level intelligence of how do I correlate all the signals in the detector to make these judgment calls of event by event. Is it noise? Is it regular? Is it physics, but not what I want? That's all sort of the data analysis aspect of it.
To learn more about the background noise, you have to have a different setup, experimental setup, so that you can actually get a model of what happens, and then take that with the help of AI to recognize what is background noise with the new experiment with a different setup, that you can learn about the background noise so that the AI knows, how to reduce, how to don't account for, those background.
Yeah. I think generally I would say this is all part of the data analysis strategy of the experiment. So for example, in the anomaly trigger, what we train over are all the events produced at the collider. Even in that 99.999% that never even make it past the trigger. There are special streams where sometimes you write out a couple of those. So we always know what the collisions look like. It's not like we throw away all of those. We save a little pocket of them so that we can study them, characterize them, and then use that knowledge to, inform what the background looks like in the actual analysis. And we also have really good simulations, in fact. It's a very well-developed simulation framework. So we have data-driven background estimation, simulation of the processes, other data sets that we can use. It all comes together to make sure we know what we're expecting at the machine. Yeah. Oh.
Yes, hi. This is an instrumentation question. Assuming that, the computation will get resolved over time, I'm curious, with the Atlas detector, the signal itself that you're detecting is probably giving us a certain response. And I'm curious if the detector now has additional sensors. I almost feel like hopefully that future collider has that baked in for, let's say, detecting gravitational anomalies and things of that nature. Do you think that's going to get sort of really interesting once you establish this framework?
So I was nodding with you, and then I had to back off with the gravitational part. But generally, yes. So the detector the detector subsystems in Atlas right now have there's certain technologies. So silicon. Sorry, I should just let this go. So silicon is one of our active technologies. It detects when charged particles pass through it. We can use liquid noble gases that are ionized by the passage of particles. There's all these different tricks, different materials we can use. And those detectors currently have a certain granularity, like how big we draw the chunks of the detector. When we look at the high luminosity LHC, when we are flooding the detector environment with more stuff, we want higher granularity so that we can better disentangle the signals from individual particles. So there are new detectors that are being built actually here at SLAC that will be installed that have more channels. When we look at future colliders, we'll be thinking about new technologies entirely, types of calorimeters or trackers that use materials that we don't use today because we came up with new ideas. There's R&D that evolves. Gravitational stuff, I think, is just too weak for the collider. Like those signals are many, many orders of magnitude weaker than the type of thing that you could disentangle here. Although, yeah, you kind of never say never, I think. But yes, we are definitely always thinking about new particle detection materials that could make more granular, better performing instruments.
Yes. So it seemed that you said earlier, I mean, in the last 50 years, we are starting from the theory and going to experiments and possibly building entire infrastructure. Now, to build the next accelerator that you talked about, the FCC, I believe, do we have already some theory that is in place that can justify actually building an accelerator that size? That's my first question.
Mm-hmm.
The other question is actually the opposite. It seems that with your approach of you start actually from the experiments, you try to isolate samples, and actually you go back to the theory saying like, do I understand all the samples to anomaly detections? And do I have the theory that backs them up? If not, then I've discovered something else. Can you comment on that?
Yeah, that's a really sharp observation, because I do think we are at something of an inflection point in the way that particle physics progresses that makes today different than the 70s, 80s, 90s, up until the Higgs discovery. Because at that time, the theory was just pointing you right where to go. It was very clear. Once we knew there was a charm quark, we thought there would be a top quark. And once we knew there was a top quark, we thought there'd be a Higgs. And you could make these observations. You knew how it would decay, you knew how it would be produced. So it was a much more theory-driven cross-check at that time. Since the discovery of the Higgs, it is kind of the Wild West. We don't know what extension of the standard model exists. We don't know its energy scale. It is a very fundamentally different moment in theory than the birth of the standard model and the decades that followed. So I think in terms of theoretical motivations for these future colliders, absolutely. I mean, there are lots of reasons why we think that dark matter should be a particle with a weak scale mass that is accessible at the collider. There's lots of theoretical reasons why we think this TeV scale, it's the scale of the collision energy of the LHC. There's theoretical reasons why that energy scale is special, why we think that that energy scale should be the next level for new physics to appear at. And the first stage of this future circular collider is what we call a Higgs factory. It's really focused on precision measurements of the Higgs. And the Higgs, because it couples to mass of a particle, is a very generic window to any other kind of massive new physics that we haven't seen yet. So I think we make these arguments based on the physics that we know is out there that we don't understand, various aspects of the model that point us to certain directions, or aspects of those existing observations that point us to certain directions, and the use of the Higgs as a portal to what lies beyond, I think are the core motivations. But I would say it is true that we are using data in a different way. All of basic science is kind of hitting this data frontier where you can take so much more data than ever before, and we can leverage that with these new tools as part of that theory experiment process, for sure.
So are you saying that with your approach, and that was my second question, that actually you don't care so much about the theory anymore? You actually just look at the data?
Simply making observations in data gets us nowhere as a field. It has to make sense. So maybe we can use the data to, I mean, if we can find things that are very unusual within the data, we would be excited, but we would have to go back to the theorists and say, what do we do with this? Like, how does it fit into the model? And then the dream scenario is you find something that's unusual, and the theorists can say, here is the path. Here is the direction we're going in. And then you can model build your heart out, right? I mean, then you can really start filling in a new version of the table. But it's going to have to come back to some theoretical underpinning, because a cluster of observations does not a theory make.
Yeah, thank you for the very excellent talks. I just have a question regarding the, say your detector, some part gets aging or, damaged, then is there any way to distinguish that from the anomalous events, or is there any plan to how to cope with such cases?
I'm happy you asked, because there's a piece of the research we're doing in the group that I didn't talk about here. So I talked about anomaly detection in the analysis, anomaly detection in the trigger. There's still the front end, right? There's still information that we can collect right at the lowest level, right at what we call the edge in fast machine learning, which is at the source, at the production side of the data. And we just put a paper on the archive, I can point you to it, about using these autoencoders, super tiny, skinny autoencoders on chips in the detector as a proof of concept to recognizing right at the sensor level if there is something wrong. And so we can imagine in a future DAC scheme where you have anomaly detection at every step of the way, you can be feeding that information up. So if you can flag that your detector cell is anomalous, it's a hot spot, or it's dead, or it's doing something strange, you can pass that on to the trigger or the DAC and say, hey, you're probably going to find this to be anomalous in your analysis, but we also registered a detector issue. And that can help you classify the categories of background, whether it's a physics anomaly or a machine anomaly, things like that. So I think there are different stages of anomaly detection application we can leverage together to help characterize what we think are weird happenings in the collider.
Thank you so much.
Yeah, thanks.
Julia, thank you very much.
Thank you.
Okay, we hope that we'll see you all for the next of these lectures. It's going to be on a very different subject, molecular analysis of the environment. That'll be at the end of January. So please watch our web pages for the exact date and time. And if you'd like to sign up for email from us about when these lectures occur, visit the Slack website and you'll be pointed to that place. So we can go, I think we'd like to clear the auditorium, but we're going to go outside, and Julia will be there for a while. You can ask her more questions. And thank you very much for coming.